Welcome back, Shaler area, to note video number 12. Today we're going to talk about chemical bonding, or how the atoms actually stick together to each other to make molecules. All right. So the takeaway from note video number 11, the last note video, was trying to develop an understanding of the elements and their electron clouds and the ways that the electrons fill up the electron clouds. And if you remember, it was divided into shells or regions or zones, and those different shells can hold different numbers of electrons. Well, actually, the innermost one can hold 2, and the rest of them, for as far as you're concerned, just hold 8. That outermost shell, the valence shell, is the one that you pay all of your attention to whenever you're looking at chemical bonding, because that outermost part of the cloud is what's going to interact with the next atom over its outermost part of the cloud. So from here on out, we're pretty much just talking about these valence electrons and what atoms will do to fill up an outer shell, because they always want a full outer shell. Because when an atom has a full outer shell, it's the most stable, which means once it gets that far, we say it's a happy atom. Remember, it doesn't have any emotions. It's not like trying to do this for any particular purpose. There's no like cognizance going on. It's just that this is the position or the orientation or the shape that has that requires the least amount of energy to hold. And things in nature tend to fall to where there's the least amount of possible energy. So this is when it's the most stable. So when one atom bumps into another, now, when you start to get to like college, you're going to realize there's a little bit more to it than bumping in. They actually have to bump into each other at just the right angles and that kind of stuff. But when one atom bumps into another, they will trade or share electrons, if doing so will result in both of those atoms finishing with a full outer shell. So if two atoms bump into each other and there's a way that they can finagle their resources and pull them together so that they both end up with a full outer shell, then you get a chemical bond. And when you get a chemical bond, that's a chemical reaction happening. It makes a molecule. So we're going to discuss 3 different kinds of chemical bonds. But keep in mind that it's a little bit like the periodic table and the elements. If you start at one side of the periodic table, like the left-hand side, you're in the zone of metals. And then as you move towards the right, specifically as you move towards like the top right, things become more and more non-metallic. So it's this continuum as you move across. And then in the middle, you have like the metalloids, which are kind of like the blending of the two. There's not just like a clear metal and clear non-metal. And, you know, they're categories that we have created to break up this continuum of existence. And the same thing happens with bonds. So we're going to talk about ionic bonds. We're going to talk about covalent bonds. And we're going to talk about polar covalent bonds. But they're really all just one continuum of energy that holds together atoms. But we've just broken them down into these different categories so that we can discuss them. So ionic bonds form when one atom essentially gives its electrons to another. So it no longer has them. Those electrons exist solely by the other atom, and they live in its electron cloud. This causes both of these atoms to become ions. All right, so now they both have charges. So one of them is going to give an electron away. If it gives an electron away, it's going to lose a negative part of it. So that atom will become positive because it'll now have more protons than electrons. And then the one that it gives it to will now have one more electron than it does protons, so it's going to be negative. So when you get this passing of an electron from one atom to another and you create these two atoms that have charges, they have opposite charges. So because of electromagnetic force, they stick together to one another. So when you have opposite ions, they can form this bond that's like a really powerful, like magnetic kind of connection between the two. This tends to occur between metals and nonmetals because it really tends to occur between things that are like far away on the periodic table. So here we have sodium and we have chlorine. Pretty famous bond here to make sodium chloride. A lot of things that join from ionic bonds make crystals because there's this regular pattern of like positive and negative that make this like ordered pattern going on of atoms in the molecule. So it can have these repeating units, and that's what forms crystals. And since these things are held together by a really strong, like magnetic sort of attraction, it takes a lot of energy to break them apart. and to make the molecules kind of like start to slide around each other. And that's why crystals and things like that tend to have really high melting points. You have to make sugar really hot to melt it. Salt has to be ridiculously hot in order to melt it. So okay. So, oh, hurry up here. All right, so sodium, which is over here, bam, right there, and chlorine, which is over here. See how they're very far away on the opposite sides of the periodic table? So this is the one extreme of bonding. So this is like an extreme ionic bond over here. So this is the sodium atom has one electron in its outermost shell. So its valence shell just has a single electron in it. Chlorine is in the 7th column, so it's over here. It's in this family. It's in the halogens. So we have an alkali metal and a halogen reacting together. And the chlorine has 7 electrons in its outermost shell, so it has this one hole that really wants to get filled up. And it really wants to fill that up, so it's going to try to steal it from anything. And this is why fluorine is like the most reactive element that there is, because we're talking about a shell that's really close to the nucleus. So there's a lot of kind of pull there, and it just needs one more. So it's like an extra amount of pull. It's like almost there, so it's really going to try to rip it off of anything. The further away, the more shells that you add, the less kind of reactive that they get. But still, it only needs one. The sodium has one in its outer shell, and it gives it away. Look at what happens. Its outer shell you would think would be empty, and you'd think that's the opposite of what you want to happen. But if it's empty, it's not the outer shell anymore. This one is now the outer shell of sodium, and it is full. See how tricky that is? So by giving one away, it actually acquires a full outer shell. And that gives the sodium a positive charge because now there's more protons than electrons. Chlorine now has a negative charge because it picked up this extra electron over here, and now they can stick together sort of like a magnet. So if you want to think about it, if we look at the second family, the alkali earth metals, they will need they will have 2 electrons in their outermost shell. And then if we look at the next row, the next column over, the oxygen family here, they all have 6 electrons in their outermost shell, so they need 2 to fill it up. So if you try to join things from the alkali earth metals and you try to join things from the oxygen family, they match up perfectly. Just like elements from this family match up with elements from this family where they only need 1. So most of our ionic bonds are going to take place in these outermost extreme ends of the periodic table. So just little, let's say we had a magnesium here. Magnesium would have 2 electrons in its outermost shell. If we try to match it up with a chlorine, right, chlorine only needs 1. Well, it would take then 2 chlorines to pick up both of the magnesium electrons. So the one magnesium electron would go to the one chlorine, the other magnesium electron would go to the other chlorine, and then you would end up with balanced out charges, and they would all stick together as a molecule of 3 atoms. I think you show that one in that Lewis Dodd homework. All right, so if it's not an ionic bond, then it's a covalent bond. And covalent bonds don't involve a giving and a taking. They involve a sharing of electrons. Now, covalent bonds tend to form between atoms that are in families that are really close to each other. So while ionic bonds, they have to be really far away from each other in the periodic table, covalent bonds happen between atoms that are in families that are really close to each other, just a couple families away, a couple columns away from each other. And now we're going to be talking mostly about the elements here in the middle. Remember, we skipped this whole region in this part. The transition metals, you'll talk about those when you get to the high school. So carbon, here right dead center, number 4, in family number 4. These always form covalent bonds. And covalent bonds tend to be non-conductive. They don't transmit electricity very well, if at all. They also have pretty low melting points because they don't have this like rigid structure and the hard attraction to each other that the ionic bonds have. So what do they kind of look like molecularly? Well, you've made this one. Here we have carbon. Carbon has 4 valence electrons, so we're only showing the outermost ring here. So carbon has 4 valence electrons. This is that like Lewis dot model that we were talking about and that we had a homework assignment on. So it needs to fill 4 spaces. Well, hydrogen has 1. It's in the first family. So you show bonds covalently by pairs of electrons. So if you remember from the happy atoms modeling kits, you would put the two atoms together so that those two arms would be next to each other. That's the bond. That's the covalent bond. So this pair of electrons would hold these two together. This one would hold these two together. This one these two, and this one these two. And by doing so, carbon now has 8 electrons in its outermost shell because it has its 4, and then 1 from each of the 4 hydrogens. So now there's 8 there. And the hydrogens have 2. They have their 1 and the one that they're also borrowing from carbon. And this kind of holds them together. Because remember, hydrogen only wants 2 because it only has 1 shell, and the first shell can only hold 2. So the way that you can think of these things actually being held together in this way, sort of think of it as like the Flash from the superhero comics, where it can run really, really fast. Well, these electrons move at nearly the speed of light. They're like the fastest particles that there are. And these atoms aren't very big. You know, these things are super, super tiny, remember. So if this thing is going nearly the speed of light, and it's going to go around here, and then go around the carbon, and then back around the hydrogen, and then back around the carbon, it's going to be doing that so fast that it doesn't give them a chance to get away from each other. A little bit like if the Flash were trying to round up a whole mob of people and just runs around them in circles. Nobody can get out because he's everywhere at one time. If they try to leave, they run into him. And that's a little bit how these electrons hold these things together in this way. Oxygen over here. So this one shows both of the rings of oxygen because we have the first row. That would be this one, these two here, the inner ring. And then oxygen is in the second row here. So it's got 2 rings. It's in the 6th family. So it's got 6 electrons in its outer ring. 1, 2, 3, 4, 5, 6. That means it needs 2 more. So if we put 2 oxygen atoms together, they can each share 2 with each other, and now they both have 8 in the outermost shell. And if you're sharing 2 pairs, that's your double bond, which is stronger than a single bond. So single bonds happen when you're sharing 1 pair of electrons. Double bonds happen when you're sharing 2 pairs of electrons. It also happens with carbon dioxide. So we have our carbon atom. It needs 4, so it can share 2 oxygens from this one and 2 electrons from this oxygen atom. Now it has 8. The 2 oxygens have 8, and everybody's happy. You can also get a triple bond, and this will often happen with elements in the nitrogen family, and this one right here in this family, you'll often see these elements forming triple bonds with things. And that's when you're sharing 3 pairs of electrons. So now both of these nitrogen atoms have 6, 7, 8 in their outermost shell. This is nitrogen gas. It's one of the reasons that nitrogen gas doesn't react with anything else, and it's so inert because it's held together so strongly by this really strong bond that it's difficult to break it apart and make it actually react with anything else. So those are the 2 extremes of bonding. So we have your ionic bond on one side, where you have a complete giving of electrons, and then the electromagnetic force kind of holding them together. And then on the other side, the covalent side, you have the complete sharing of electrons. Well, in the middle, you get this polar covalent bond. And polar covalent bonds happen when they share, but they share in such a way that one of the atoms has the electron for a longer amount of time than the other. So if you're talking about atoms that are significantly different in size, or if you're talking about stuff on really, really big, long molecules, that things can happen where electrons just spend more time around one end of the molecule than the other, you get this polar covalent bond, and this literally turns the molecule into a magnet, or at least it behaves like a magnet. You have charged ends, sort of like a North Pole and a South Pole on a magnet. And this can cause really interesting interactions with other matter, because sometimes matter is attracted to things with charge, and sometimes matter is repelled by things with charge. There's stuff that like water, there's stuff that doesn't like water, and all of these different interactions between molecules cause all the stuff that we see in the world around us. So water is a really good example of a molecule that has this polar covalent bond, and water has such a big influence on everything on Earth. So oxygen's a much bigger atom than hydrogen is. So the electrons spend more time around the oxygen than they do the hydrogens, and this gives the oxygen a negative sort of charge to it. It's not a full negative charge, but it's this like negative end. It's got like a negative tinge to it, and the hydrogen sides have a positive tinge to it. And this causes the molecules to kind of behave in certain ways, and this is actually one of the things that makes water have such a super high specific heat, because these water molecules, when you get a whole glass of them, for example, interact with each other, and they kind of strengthen the connection between each other. This is one of the things that gives it that that surface tension that's pretty strong. It can take in a lot of thermal energy before the movement and the buzzing of these things is enough to overpower this like charge effect that it has going on. So that's why the temperature doesn't really change. So these polar covalent bonds have really interesting interactions. The one that you're really going to need to know about is detergents. So these are soaps. The reason soap works is because one side of the molecule does not have a charge on it, and the other side of the molecule does have a charge on it. So if you remember from 7th grade, one of the materials that living things are made out of is called lipids, and lipids are your fats, your waxes, and your oils. So if you remember, there was water, nucleic acids, nucleic bases, proteins, lipids, and it's also what makes up like your cell membranes and that kind of stuff. So if you remember drawing pictures of cell membranes in 7th grade, they may have looked like this. You may have had a ball on one side and like a stick on the other. And if you looked at actual molecules of lipids, and if you looked at like the chemical structure of them, you would have seen these really long chains of carbons. So lipids have these really long carbon chains on them. This isn't a lipid over here, but it looks just like this. You actually make, this is soap, and you actually make this from lipids. I've always wanted to do the lab in class where we start with like some kind of animal fat and we turn it into soap. That's how soap is made. So you kind of take these long tails and you stick another molecule on the end of it and it becomes soap. So how it works though is water, since it has a polar covalent bond, likes to stick to molecules that have a charged end on it. And it does not like to be around molecules that don't have any kind of charged ends. And lipids don't have any kind of charged ends. Well, lipids are your fats, your waxes, and your oils. This is why oil and water don't mix. They stay away from each other because they don't kind of connect because of the way that one has a polar covalent bond and the other one does not. So with soap, you end up getting these charged ends, the ends with this molecule over here that has a charge on it, on the end of this long chain of carbons. This side likes water. So it's going to arrange itself so it's touching water. These long ends don't like water, so they're going to arrange themselves so that they don't touch the water, and they end up making these tiny, super small bubbles. But on the insides of the bubbles, you have the dirt, because dirt is made of things like lipids. It's chemically very similar to lipids. And this is why the soap will wash the oil off of your skin, because the long ends will stick to the little globules of oil, while the charged ends on the outside stick to the water, and then it ends up washing it off your face and down the drain, taking all the dirt and everything with it. So it's pretty neat. It all comes down to the shape of the molecule says everything about its behavior in the world that you see. All right, that is it for note video number 12. So we have ionic bonds, where they give and take electrons. We have covalent bonds, where they're sharing electrons. We have polar covalent bonds, like soaps, where they kind of do a little bit of a blend of both. All right, you have a nice day. I'll see you at school.